Hi everyone. So this is Anvita Bansal and today we are going to discuss this topic, understanding and implementing binary trees. So before we move ahead, we'll go ahead and understand what is binary tree, what are the types of binary trees, what are nodes, some terminologies related to binary trees, and how do we implement it, or in short, how to create a binary tree. So let's understand this thing. Oh, moving to my whiteboard, have a look here. So, what is binary tree? First of all, it's actually a non-linear data structure. You must have heard about arrays, you must have learned about arrays and all those data structures. So, binary tree is a non-linear data structure. Now, what is the structure of this actually? So, you have a node, let's say you have a node here, and this is your parent node, let's say N1, that's your parent node. N1 has certain children. Okay, those are its children node. Let's say N2, N3. So what you see here is that N1 has two children. That is why it is a binary tree. If it has more than two children, let's say it had N2, N4, N3. So it has more than two children, can have many children, as many possible. So that will become an array tree. But here we'll be discussing about binary tree. That means a parent having at most two children. Okay. Then further, each children can have its own more children, right? So N2 can have N4, N5, N3 can have N6 and no right child. Then N6 might have one more child, let's say N7, and then one more right child, N8. Let's say N4 has another right child, N9. It can be in any order, left child, right child, but at most they can have is two number of children. One will be known as left child, the left one is left child, the right one is right child. Okay, and the parent, this is known as parent node. Okay, now understanding the number of nodes, the number of children at each node that it can have, let's have a look here. So in a binary tree, at each level, the maximum number of nodes that you can find is 2, and the minimum number of node will be 0. Either it can have no children or it can have one or two children at max, right? So when we talk about this, see here, this is, let's say, 10. Okay, this is your parent node. 10 has further 20, then it has further 30, it has further 40, 50, let's say it has 60, it has 70. Okay, so let's consider it as 0th level. Okay, this is your 1 level, this is your level 2. Okay, let's extend this and make it 80 and 90. Okay, so let's consider this as level 3. Now few things that you should know here is, first thing that I'm going to talk about is the depth. So what do you mean by depth? Depth is actually the edges from that node to the root node. Few things I will write here. Root node is your only node which is known as parent. This is the root node, right? For this tree, this is your root node. 10 is your root node. Here 10. Then you have child node, left child, right? Left child. Then you have right child. Okay. Now if you see here at level 1, how many nodes do you have? You have total 2 nodes, right? You have, I'm writing it here, you have total 2 nodes. How many nodes? I'll write it in different pen. How many nodes do you have at level 2? 1, 2, 3 and 4. So you have 4 nodes here, right? You had 2 here, you have 4 here. At max, right now we have 2 nodes only, but let's say if each of the leaf node, also one more term, leaf nodes. Okay, I'll come on each of them one by one. Let's say if all of these nodes had their own children, left child and right child. Okay, it also has, let's say, so what are the maximum number of nodes that you can find at this level? So it will be 1, 2, 3, 4, 5, 6, 7, 8. So this is 8. So do you see a pattern at every level? See, 2, here you have only one node, right? This is your level 0. You have only one node, which is 2 to the power 0. Then at level 1 you have nodes that is equal to the, your level is 1, 2 to the power 1. Then here you have total 4 nodes that is equal to 2 to the power 2. Then here you have 2 to the power 3 number of nodes. So what do you see here, that at every level, at each level, let's say each level, the height of that, or you say depth, maybe you can say here depth. If depth is equals to h, let's say, okay, so the maximum number of nodes, maximum nodes at that level h will be equal to 2 to the power h. You see that? So only considering, if you say that this is your 0th level, this is your first level, this is your second level. If you want to consider this as level 1, then it will be 2 to the power h minus 1. That's how you will treat it, right? So this is 2 to the power 2. So it will be, but actually it doesn't go that way. Your calculations will become a bit tedious in that way. So this is how you consider your depths. Now, difference between these terminologies, depth and height, is from each node. Let's say you are at n4. Okay, for n4, how many edges do you connect with your root node? Do you see edge 1, edge 2? So there are 2 edges that connect you to the root node. So depth for n4 is 2. N4 depth is 2, right? Similarly, n5 depth is also 2. What do you think for n3? Since you have only one edge connecting to your root node, your depth will be 1. Now talking about height, if I talk about height is considered for the entire binary tree. Height of this binary tree will be what? The number of edges from the deepest node to connecting the deepest node with the root node. So this is your root node. If you see the deepest node is n9 here, let's say. Okay, so n7, n8, n9 all are at the same level. So no matter which node you consider as the deepest node out of these 3. So what is the maximum number of nodes connecting you to the root node is 1, 2, 3. So that is the height of your binary tree, right? That's how you consider. And depth, you can consider depth for each node. Like the at this level the depth is 1, this level the depth is 2, this level the depth is 3. Understood? So these are the terms. Let me write it for you again. So what you saw here is number of nodes, maximum number of nodes at level I, let's say, will be equal to the 2 to the power I, right? At 0 you have 1, at level 1 you have 2 to the power 1, 2, at level 2 you have 2 to the power 2, that is 4. Also, if you see that at each level, you can say that it is almost, if you are at level 2, so and you compare with the level 1, so you can always see the difference, that the number of nodes is almost twice the number of nodes at the previous level, and vice versa. If you see at the level 1, the number of nodes will be half the level, the number of nodes present at the next level. So that's how you do it, right? And then what else can we see? We discussed about the height, right? We discussed about depth, right? Then number of nodes, height, depth, left child, right child, and your root parent child. This is about your binary tree. Now we will see here the types of binary tree. What are the types of binary tree? Let's see here. Types of binary tree. So starting with, let's see here, full binary tree. Then you have your complete binary tree. Complete. Then you have your perfect binary tree. Perfect. Then you have your balanced binary tree. You can have some skewed binary trees, or you call them degenerate binary trees. Okay, fine. So understanding these binary trees. So the difference among all these binary trees is on the basis of their formation in the nodes. How you see here, full binary tree means that each node either has 0 children or they have 2 children. Each node either this is the number of children I'm talking about, either they have no child or they have 2 children, no in between. Now let's understand from an example here. Let's say this is your 10, this is your parent node 10, then you have 20, then you have 30. Okay, so parent node 10 has 2 children, 20 and 30. 20 has 0 children, 30 has 0 child. Now if I create more children for 20, let's say left child is 40 and I create right child as 50, is this still a full binary tree? Is this still a full binary tree? Yes, it is. Why? See, you check for every node. 10 has 2 children. I'm writing number of children here. 10 has 2 children, right? 20 has 2 children. Okay. 40 has how many children? No child at all. 50 has no child at all. 30 has no child at all. So we have not found a single node here which doesn't have either 0 or 2 children. Nothing in between, either 0 or 2. That is your full binary tree. Okay. Now coming on to complete binary tree. What do you mean by complete binary tree? Have a look here. 20, 30, 40, 50. And then let's make it 60 also. Okay. So what you see here is in complete binary tree, all the non-leaf nodes are completely filled, which means that all the non-leaf nodes will have all the 2 children completely filled. But what about the leaf nodes? Leaf nodes may have no children, 1 children or 2 children, but in a way that you start filling from the leftmost node. Now when I give you this example, you will understand it better. 20, 30, and this is 40. So actually both this one and this one, both of these trees are complete binary tree. See here, this is the leaf node, right? This is the leaf node, this is this node 20 has 40 as one of its child. And if let's say I make a child for 30 as well, is it still a complete binary tree? No, it is not. The reason is, if you want to fill the leaf nodes, you have to fill it in such a way that you first complete the node which comes on the leftmost side. So if 20 is not filled with all of its children node, you cannot go ahead and fill the other node with its child. Okay, in that case it will not be a complete binary tree. So if you wanted this to be a complete binary tree, you can make it in this way. 10 has 2 children, okay. 20 has 2 children, 30 has no children, that is fine. Now even if 30 has 1 child, 60, that is also still a complete binary tree. Why? Because all the nodes are already filled which were towards its left, right? And the non-leaf nodes are already filled, that you can see here. 20 and 30 you fill with 1 left child, that's okay. That is still a complete binary tree. Is that okay? Fine. Coming on to perfect binary tree. As the name suggests, in perfect binary tree, what happens is that all the leaf level nodes are at the same level. All leaf level nodes are at same level, which means something like this. And obviously the non-leaf nodes are completely filled. Have a look here. 10, 20, 30, 40, 50, 60, 70. This is a perfect binary tree. Okay, if you see an example like this, 10, 20, 30, 40, 50, this is not a perfect binary tree. Why? Because all the leaf level nodes are what which do not have further children. So 20, 40, 50, they are not at the same level, they are at the different levels. This is the reason it is not a perfect binary tree. So perfect binary tree needs to have all the leaf nodes at the same level. That's the major condition. Then coming to the next balanced binary tree, let me erase this one. So balanced binary tree means that, try to understand, that the difference between the heights of your left and right subtree should be less than 1 or equal to 1, which means it can be either 0 or it can be 1, but not more than that. What did I say is the maximum difference between the heights of your left and the right subtree should not exceed 1. Have a look here. 10, 20, 30, 40. This is 50. Okay, then another case I have 10, 20, 30, 40. Other case I have 10, 20, 30. Okay, or maybe you can take another 40, and let's take one more as 50. Both are kind of same only. Let me draw 60. Okay, so let's take 3 examples here. First, let's see this. So the left subtree and the right subtree. The what is the height? See, number of, you see the number of edges to the root node 1, 2. Here it is 2 for the left subtree. Here it is 1 for the right subtree. So the difference between the heights of both the left and right subtree is maximum 1. So this is 1. So I can say this is a balanced tree, balanced binary tree. Now have a look here. What is the height of the left subtree here? It is connecting with the root node by maximum of 1 edge. Here the leaf node is 50. This is the deepest node, right? Deepest node for your right subtree, and this is your root. So the maximum number of edges is 1, 2, 3. So 3 minus 1 is 2. This is not your balanced binary tree. Okay. Now coming at this, so that the deepest node in the left subtree is 50, right? 50 has 1, 2, 3 edges. So the height of the left subtree, let's consider it to be 3. Now when you are at the right subtree, this is the deepest node and it is connected by the root with maximum of 2 edges. So 2. So 3 minus 2 is 1. So I can say this is also a balanced binary tree. This is also a balanced binary tree. And this is not the balanced binary. So I hope you have understood these terms. These terms mostly come when you sit for a DSA round or the online test round, and there you have MCQs. So mostly they give you examples like this, although not so direct. So you need to have this much understanding and you will be able to solve such problems as well. But you need to know, many people solve lots of questions of binary trees, but they're still not aware of what is full, complete, perfect, or these kind of binary trees, and how do you calculate the height or all those things. So these terminologies and what all things we are discussing today, these are the very basic things. Now tomorrow onwards, whatever problems we'll be solving, we'll be actually making use of these terms, or somehow you making use of these logics, implementing these logics, and we'll solve good problems tomorrow on. But for today, you need to have this basic understanding for binary trees. Okay. Now coming on to next thing, that is degenerate. I'll just quickly erase it all, degenerate, and then we'll move to how do we implement. Okay, so talking about degenerate, it is actually not much discussed here. Why? Because degenerate means it has only one child. It can be left or it can be right. Let's say this is your parent child, it has left child, only one child. 20 can have only 30, 30 can have only 40, 40 can have only 50. So this is a degenerate kind of tree, and it is actually, it makes use in linked list. That's how we define linked list, right? With pointers pointing to the next one, or there also we have different types. So this is how a degenerate tree looks like, because it has only one subchild. Now coming on to the left skewed, they are left skewed trees. From degenerate only we have formed this left skewed and the right skewed trees. Right skewed. So as the name says, left skewed means all the children are towards the left side, which means only one child is present and all of them are in the left side. 20, 30, 40, 50. And so is the case with right, just the opposite, 20, 30, 40. So these are the types of trees that we have discussed right here. Okay. So now coming on to how do we create a tree? Let's see here. Let me draw a tree first of all. 10, 20, 30, 40, 50, 60, 70. Okay, let's say this is our tree. Now, what do we have? What do we have here? It's actually each tree comprises of what? The data of the node, right? The data of the node, then the address of its left subchild. Let's say triple two. Let's say triple three. Okay, and so is the case with the others as well. This is the data of the node itself. Then it stores the address of the next left child which it is connected with. Let's say this is triple four, this is triple five. I should have made it a little bigger, but don't worry, I'm going to come on this topic again. Now, since 40 is the leaf node, it has its own data, but it has no left or right subchild. So the address will be null at both the places. So this is typically what a node in a tree comprises of. It has three components. It has three components. What are those? The data, that is the value, or you can say data of node itself, right? Then it has left node, and it has the right node, which is actually the address of its left child and the right child. Okay, so this is typically what is comprised of within a node in a tree. Now, if you see, trees can also be implemented using array, although it has very less usage because of the reasons which I will tell you right now. If let's say I want to implement this tree itself using an array, how am I going to do that? Can you think of it? You imagine I want to store all of these nodes in an array. How can I do that? Let me draw an array of, let's say, how many nodes we have? 8 nodes we have, right? 7 nodes we have. Let's draw an array of size 8, because array is, whenever we define an array, we have to define the length of an array, right? So it has to be, because that's how arrays are, and this is one of the reasons, since we cannot dynamically add, subtract, add or delete the nodes of a tree if we use an array, because of the size that we are taking. This is the reason that this becomes limitation. So I am drawing it of size 8. No matter, we have 7 nodes. 1 2 3 4 5 6 7 8. Let it be 9 also. 1 2 3 4 5 6 7 8. Okay, so for the creation purpose, for the creating this array, we will not fill up the 0th node because of the calculation reasons. I'll tell you why. Because we are simply using a simple maths here to calculate which position that left child and right child of a particular parent node is going to be. For those calculation purposes, we are not going to consider 0th node. Let's fill up 10 at the position 1. Okay, 10 at position 1. Tell me the left child of 10, that is 20. Right child is 30. Now I've filled up root node 10 with its left and the right child. Now I want to fill up with the left and right child of 20 if I have it. So I have 40, I have 50. That's how I'm going to linearly place it in an array. Then I have 30, left child is 60, right child is 70. That's all. That's the end of your putting up all the nodes in an array. Now, how do we access the nodes? If I ask you, where is the left child of, tell me, 20. So will you be able to tell me which index it is present at? So let's say this is your level 0, this is your level 1, this is your level 2. And in an array, as I told you, when we are not filling 0 because of this reason, for the calculation point of view, we will take it as level 1, level 2, level 3. Now if you see, 20 is present at 2 cross 1 index, right? That is 20 is present at, let me write it this way, 2i 2 into I plus 1, where I is the level of your parent node. See, if I want, I know I have filled 10 at first index, right? Now 2 into 1 is 2 is the index where your left child will be present. Left of 10 will be present. 2 into 1 plus 1, that is your index 3, is where your right of 10 will be present. And I is what? I is the level, or the, not level, here we are considering an array, so we'll go along with the index of array, is the index of that root whose child you want to find out. Root node. Okay, root node of whichever node you are at. So if my I is 1, my parent is, let's say, 10, so the left of 10 will be at 2, and the right of 10 will be at 2 into 1 plus 1, 3. Similarly, let's say now this index, at index 2, this is my parent node. I want to find the child of 20. So this is present at 2 into 2, 4. This is where 40 is present. Now at index 2 into 2 plus 1, that is your index 5, is where your right child is present, right of 50. This is left, this is right. Now for 30, I want to see where is the left child. So ideally it should be at 3 into 2, right? At 6. So that is the case. Yes, that's the case. This is the left child of 30. Now at 7th index, we have the right child of 30. So that's how you calculate it. Okay. We are not going to implement it because this is how I have already shown you that how you calculate the indices of the left and right subchild. 2i for left, 2i plus 1 for your right. You can try it on your own, but it has very less use case, because when we want to, let's say I want to extend my tree. I want to extend my tree with 80, 90, 100. It doesn't have to be in this order the way I'm writing it, 80, 90. It can be anything, 253, 72, and anything. Now what? You already have defined an array of size 9, right? But my the count of my nodes is more than that. So what are you going to do? You're going to create another new array, or you are going to, how do you extend the space? Maybe, okay, you will take some array list, but this is the reason for it. We have to insert the nodes dynamically. For that reason, arrays would not work for us. Okay. Now coming on to its implementation, linked list implementation, or the node implementation, which I just gave an overview at this place. This is how a node is, right? Node has its own data, and in this case for a tree, it has two more things apart from its own data: address of the left subchild and the address of the right subchild. So let's have a look here. So we are done with the array. I have just shown you how array can be used to store these tree nodes if you want to. So array is done. Now let's see linked list implementation. Linked list implementation of a binary tree. So what do you create is you create a node. Okay. I would like to show you while coding so that you can understand it better. 40, 50, 60, 70. So you have a node. Okay. You have a, let's say you have a class node. You define a class node which has what? Which has its own value in data. Two nodes, one is left for the left child and other one is right for the right child. Okay, this is what you do. Then you want to also let's say we are initializing the data using its own constructor. So you define a constructor node, let's say static node or whatsoever you want to. We'll write it in code. And this dot data equals data, and here itself you can also initialize left with null or and right with null. I'm not doing it here, you will do it right also null. This is how we are initializing it using the constructor, right? So this is my class node, okay, which has what this class node has defined. This is the definition of node that I'm giving, okay. It has its data, it has left child, right child as the nodes, and then I'm initializing it. This is what I'm doing. Now you go ahead and you try to create try to create this tree. You want to add left, right child, that we will see. Before we go ahead, see, actually this is the end of how you create a tree node. This is how you create a tree node. But if you want to see how you give input and how you create a tree, and you want to see that in the console, that also we can do. But actually this is the entire work that you need to understand. How do you create a node class, then you define the data, then you define the left and the right node child, okay, and then you initialize this node. Fine, this is the main task. Now other thing comes up as I can go to my main method, and simply, let's say I give a data 10, and I can do it 10 dot left, I can give another data 10 dot left is 20, and so on. And you can visualize that you have created a tree, something like this. Now this is about creation. Before we go ahead, I just want to tell you how do you there are lots of operations that you can perform on a tree. What are those? First, you have seen that we will create it, then insertion of a node, insertion of node. That's what we will do in creating the tree, insertion of node, deletion of node, deletion of node, deleting a binary tree entirely can also be a thing. Then traversal, okay, insertion, creation, deletion, traversal. Now when we talk about traversal, there are two types of traversals: breadth first search and the also there's searching. Sorry, before traversal, let me tell you, there is also searching that you do in the binary tree. In what ways can you search a node in your binary tree? Let's say you want to search 20, how will you search 20? So these are some things, okay. Breadth first search, depth first search, okay. Now searching BFS, DFS, depth first search. When we talk about BFS, I will tell you in coming lectures where we will discuss about level order traversal. Now we are not going to go ahead and discuss about the topic itself. In fact, we will solve problems that will utilize all of these things. Level order traversal. Level order traversal is traversing the tree level wise. First I am traversing at 10, then I am giving 20, 30, then 40, 50, 60, 70. This is how you traverse in breadth first search. Now traversing in depth first search is of three types, which we will discuss. One is pre-order, in order, and post order. I'd like to give a brief about pre-order right now. Pre-order is like, let's understand, you are traversing a tree from the root node, right? You traverse 10 and you print, just let's say you print 10. Now which node you will travel to next? You will travel to the left of 10, that is 20. Now you are at 20. Just assume that there is no other tree. Now you have a tree which is associated with 20. What tree it is? It is this subtree, let's say. So 20 has its own left child. Now I will go to the 20's left child, that is 40. At each step, actually I am repeating what I am doing above. For 10, I was traversing to 10's left child, then 20 becomes my new root node and I go to its left subchild, that is 40. Now when I'm done with traversing to all the left childs, I go ahead and ask 40. 40 was called by whom? 40 was called by 20 as its root node, right? So 20 I've already traversed. When I was at 20, I already printed 20. Then I went to its left. Now I have already printed 40. I go to its left. I do not find any left child. That is why I return back and I go back to from where it was being called. This is what we are going towards recursion. When I'm discussing this thing, this is what we are discussing about recursion. We'll get an idea about recursion. So when I go back to 20, I see that I've already traversed its left child. Now I will traverse its right child. Do I have its right child? Yes. So I will print 50 now. Now consider 50 as my new tree now, new root of the tree. So 50 has any left child? No, it does not. So I will return back to the node from where this left was called. Left was called from 50. 50 has any right child? No. I'll return back to the node from where this right was called 50. Now 50 has made its call to left and right. Now it will be returned from where it was called. So 50 was called by 20. Now since 20 has traversed towards its left subtree, right subtree, 20 itself will return to the node where it was called. Now it was called by 10 as part of the left subtree. And 10 we have already printed, because whenever we go to a node, we first print it or we return as one of the outputs, and then we traverse the left subtree and we repeat the same step. And the last part which we traverse is the right subtree. Now I go to the tens right subtree, which is 30, 60, and 70 here. So you see a pattern. Now 30, 60, 70 is another new tree for us. Let's consider, which has root node as 30, which I will print here. Let me write this print here. So 10, 20, 40, 50. Then we go back to 30, right? Now you see here, see, we were at 30. Okay, tens right is 30. But when we see 30, we go and check for its left subtree, and 30, 60 is at its left. It will return when it sees it has no children ahead, it returns back to 30. And does 30 have any right child? Yes, it does. We go and print, and then we return it from here to this subtree, and we see that left and right traversals are done. We return back to the root node which is called it, and now we see all the traversals for this tree has been done. What was the pattern of a traversal? Was we first go to root, then we go to left subtree, left, and then we go to right subtree. So this kind of traversal is known as pre-order traversal. Pre-order traversal of a binary tree. Pre-order traversal means you go ahead from root, then left, then right. So if I ask you to traverse this subtree 10, 20, 30, 40, okay, 60, 70, how will you, what will be the output if I ask you to print it? So it will be something like this. Let me delete this one. Okay. So see, first I will print 10, then 10's left is 20, 20's left is 30, 30 does not have any left. So I print its right, that is 40. See, 10, 20, 30, no left child. I go ahead and print 40. Now this is done. I go back to 30, then I go back to 20. 20's right. Do I have any 20's right? No, no right of 20. So I go back to 10. Now I traverse to 10's right as a whole. Now when I go to 10's right, I find 60. I will print 60 here. Now I will check for 60's left child. Does it have? No, it does not. Then I go and print 70. So this is how you traverse a tree in pre-order traversal. Pre-order traversal of a binary tree is this, right? So this is root, left, and then right. And similarly, now you can understand the in-order traversal is left, then root, and then right. Left, first you go to left, then you go and print right, a root, and then you print right. So if I want to traverse this in order way, what could it be? I see 10, but it is the root node. I go to its left, 20. I go to its further left, 30. I go to its left, null. So then I go back to 30 and print it. After 30, I see that 30 did not have any left, so I printed the root itself, and then I go to its right child, which is 40. So basically, if you see for 20, its entire left portion is completed, right? So now you print the root itself, which is 20. Then you go to the 20's right, which is nothing here, null. So if you see from 10's point of view, your entire left subtree is covered and has been printed. So now you are at the root itself. You will print your root. So this will be 10 here. Now you go to the roots right. This is what is present in roots right. So roots right has other subtree which has 60. This is the root in itself. You'll go and find its left, which is nothing here. So you'll print nothing, and then you print the root itself for this subtree, which is 60, and then you go ahead and print 70. So this is your in order traversal. I hope you have understood this. So today itself you'll understand this traversing pattern of traversing. We will then in further lectures and in further all those live sessions, you will directly go ahead and actually not exactly implement. We will be solving good questions which will make use of these implementations. That is why just understand all of these terminologies and how we are traversing it. This is very important. So this is your in order traversal. See, the thing that I told you, creating node and what all data it has data, it has left and right child. This is nothing, just this block of code is required, and that too when you will solving problems that have been asked in interviews. Like, there are lots of problems that we'll be going ahead with tomorrow. You don't even need to actually create this class node. You don't need to, that will be already created. You'll just need to write the function. But I do not suggest you to not go ahead and try, because you need to understand how your binary tree is getting created. So that is why I'd suggest you to do that thing. Now coming on to post order traversal. If I want to traverse my tree in post order manner, what would it be? As I told you, post order is, you can easily guess, it is your left, right, then root. This is how you are traversing it. Let me delete it. Okay. So I will just also create a nice tree, or if you can see from there, we can simply traverse it in post order manner. Let's try. So the post order traversal for this tree would be what? Your left, right, and then your root. So I go ahead. First, I see my root node, which is 10. Root's left is 20. 20's left is 30. 30's left is null. So you print 30 first. Then what? Actually, not even 30. Mistaken here. When you are at 30, you check for its left, it is null. Then you check for 30's right, it is 40. So you go and print 40. Okay. Then you see 40 has no left, right. Already, actually, when you printed 40, you already checked for its left, then you checked for its right. Both were null, then you printed 40. Now 40 will return this value to 30. And since 30 is the root for this subtree, you will print 30 now. Now you have printed actually the left portion for 20. Now you will check for 20 dot right. It is null. So you do not have anything to print. You will print the root itself, which is 20. Okay. So for 10, you have printed the left subtree. Now you go ahead and check for 10's right part. 10 dot right will give you 60. Okay. And now you will check for 60 dot left, because left, right, root. 60 dot left is null. So you will come back to 60 and check for 60 dot right, which is 70 here. So you will print 70. And then you will go and print 60, because 70 does not have any left, right. Then you printed 70, and this returned value to 60. Now you are at position where 60 is your root for this particular subtree, and you print 60. Now 60 is printed. So if you check from tens point of view, your right subtree has been printed, your left subtree was already printed. Now only thing to print is your root node itself. So this is your post order traversal of the tree. Understood? So these are the things that you need to understand for binary tree. And if I want to summarize this, we can, let me see if you can see my screen, and fine, I think you were able to. So now comes to the last, actually nothing is left. Now we can summarize simply if you want to summarize it. So we discussed about binary trees. Okay. Binary trees, what is a parent, child, okay, then what is the difference between height, depth. From here only I just recall of diameter, okay, which also has its good question which has been asked in interviews. We will solve this problem, then you will understand how you calculate the diameter of the tree. Then we discussed about, okay, maximum number of nodes at any level, okay. Then if you know the height h, let's say, then you can calculate the maximum number of nodes. That will be 2 to the power h minus 1 at max, total number of nodes in a binary tree. And then we discussed types of binary trees, okay, fine. Then what we discussed, then implementation using, we just understood this, not that we coded it, because it is of actually no significance as of now, especially of array implementation of binary trees. But you need to know how you can implement it. Many people don't recall that, okay, array is also one way in which you can implement binary tree. But why we came to linked list method? Because it has its own limitations. So what are those? We saw array implementation and we saw linked list implementation, okay. Then you saw that in array, if you want to find that left child is, if you know the index of your parent child, you can calculate the index at which your left child is present and index at which your root child is present. Then in linked list, important part that you need to see, you need to understand the basics, the formations, okay. Then there's nothing left in coding, and after you put the right logic behind it. So what is the node comprising of? So let's say this is your parent node whose value is 10. It has the address of its left subchild. Address can be anything, like let's say 222.333. So this is the left subchild's address that it points to. It is the pointer which is containing the reference, which is containing the address of your left subchild. This is the address containing your right subchild. Let's say it has 20, which is your left child, and 20 has a left child, let's say. So that address is, let's say, 444. It has some left child which is 30, which further has no child, so it will be null. And 20 has, let's say, no right child, so the address will be nothing, null here. So this is how you create a node, right? You create a class node, you actually define this data, and then in the constructor you initialize it, and left node, right node, and so on. Okay, I'm not writing it again. Then you saw implementation, and I think that was all. What was it? Then operations that we can perform, operations that you can perform on a binary tree. That there are lots of operations. You don't have to worry about these things. We will all obviously going to solve questions on that. And then what we saw, operations, and I think that's all. Yeah. Then you saw traversals. Traversal is an important part which we will solve tomorrow onwards. Traversal was pre-order, in order, and your post order. So this is the end of today's lecture. But before we come tomorrow again and start solving problems, I just want to tell you that you need to do certain things from your end, which is, first of all, if you are very naive to this, what all things we discussed, go understand and try to take some examples and compare. Take examples of complete binary tree, then perfect binary tree, balanced binary tree. Try out some trees and see if you are able to figure out which is what and which is not. Then traversal, in from traversal point of view, I'm not asking you to code anything, that we will do. I'm just asking you to make these concepts very clear. For pre-order, just take a binary tree and you yourself start traversing the tree and write the output. So in your traversal, what output you are finding, just compare it with the right output, so that you may know that you are able to traverse the tree in the right manner it is supposed to be, right? So that was all about today. And now we are going to solve the questions. Tomorrow onwards, we'll directly take some very good problems that are frequently asked in interviews and companies. So that was all about today. See you all tomorrow. Thank you. Let me see if you have any comments. Huh. Coming on to your comments, okay, time complexity. When we talk about the time complexity, see, there are different operations, and according to that, we will be discussing about time complexity. Since today we discussed about how we create an array. So in an array, it's the total number of nodes, and that is the amount of space that you are taking. So space will be of O(n), and same is the time complexity. You're traversing each only once. And same with the traversal also, which we discussed. Since we will be discussing about it recursively, if you, all these traversals need you to have good grasp over recursion, but if even if you don't know, don't worry, we will discuss it. So the time complexity recursively, we will be discussing it, how it's log n, or where n is the number of nodes. So this is how, I think when we discuss the question, that will be the best way, where I will tell you how your time complexity is varying from problem to problem. I think that was all. If you have any doubts, you can write in the comments. We will be using Java. I'll also write it in the comments. The language you're going to use is Java. If you have any more doubts, you can write it. And then we'll wrap it up. Thank you then. See you all tomorrow.